Okay, welcome everyone to this pseudo talk of mine. So what happened is I really gave the talk I'm going to give in this video as well. I gave it live, but kind of the recording crashed. So I'm going for something new. I give afterward recording talk of a live talk, which in some sense is probably better anyway, because the quality would have been pretty shit for the live talk. Not saying the quality is much better now, but hopefully a little bit. The only thing we lose is kind of the flavor of a live talk. So this won't be really live, it's a recorded talk, right? So anyway, I kind of will pretend that this is a live talk. There won't be many questions, obviously, because I'm recording this, sitting here very alone, which is not so bad, but anyway. And I'm not trying to simulate questions by asking myself questions. I'm very sorry for that. Maybe that's the next step I do. Anyway, so this talk was about categorifications, objects, and their shadows. And I hope you will enjoy it, because it's kind of at least my biased point of view, one on what categorification is, which is essentially my field of research. And I will focus on, well, homology and actions, the two parts of categorification I'm attracted to the most. And for me, well, if you don't know what categorification is, welcome. This should be your talk, hopefully. For me, categorification is really this picture that you have a rich object somewhere, like a sphere, up here. And what people have seen for years is kind of the decategorification, which in my little example, I should really give it a different color here. My little example down here would be somehow the slices, the shadow of the object itself, which is a less rich structure. So going from upstairs to downstairs, that's a process called decategorification, is pretty easy, but going the other way around is the whole point of categorification. So categorification is kind of an easy one-way street and a very difficult street the other way around. And I'm trying to motivate it a little bit along the history of the field. So I hope you will enjoy it. So kind of for me, categorification in a nutshell is really kind of two representation theories, some version of categorical actions, categorification itself. And for me, it's really crucial to develop the theory while focus on applications. Some people would disagree with that. Some people just like applications. Some people just like the theory. Probably some people also like neither. But I'm kind of in this little Venn diagram, if you want. I'm kind of in the intersection of, well, this was a really bad arrow. Let me try again. I'm kind of in the intersection of application and developing theory. So here are upstairs you find, so categorification is fairly new. So you might wonder what is it actually? But here upstairs you find some applications of this field. So which is roughly 25 years old by now as a field, maybe even only 20 years as a field. And it has a lot of applications. Some of them I'm going to touch upon a little bit, and some of them are pretty new and take place in, well, non-math subjects. So it's kind of a real-world application. Cybersecurity, if you want to call cybersecurity a real-world application. Machine learning, artificial intelligence. And maybe more classically, something like low-dimensional topology or representation theory. And I'm going to sketch a little bit how I think about categorification, and hopefully you will enjoy that as well. That's the whole point why I'm re-recording this video. I'm just kind of being a little bit pissed with myself that I messed up the first recording. But anyway, let's not come back to that. Let's rather stay with the maths. So categorification is this idea essentially of replacing a set theoretical structure like a number by a higher categorical structure like a vector space. We might say, well, whatever. And categorification kind of reveals hidden properties. So we'll see several of those as we go along. It's really like the shadow versus real object picture, right? So here in my little picture, categorification itself is the knot. And what you see on the wall, shadow, is kind of the classical story. And really, categorification is essentially all about this picture because it really makes kind of connections visible. So if you don't have enough structure at hand, it's sometimes hard to tell whether there's really a connection. Maybe you just have two matching numbers or something. So it's not quite clear to say why field A, which spits out the number, and field B, which spits out the number itself, should be related. But if you instead of a number have a category or something even richer, and they both spit out the same, then it's kind of easier to kind of connect over the strings. And my little example here of categorification, maybe the classical one, is a categorification of the natural numbers, which I've drawn as a little blob down here. So natural numbers, my favorite numbers, so 1, 2, 3, 4, 5, whatever, are down here, and they are categorified by the category of vector spaces up here. So 1 goes to a vector space of dimension 1. 2 goes to a vector space of dimension 2. And the easy way, the decategorifying way, is just taking the dimension and going downstairs. And why is it a fabulous categorification? Well, first of all, everything kind of goes nicely. 3 goes to a 3-dimensional space, 6 goes to a 6-dimensional space, but also standard operations are categorified. Addition goes to direct sum, multiplication goes to tensor product, having lower or smaller goes to surjective or injective. So that's great. So all the standard structures we like about natural numbers, they live upstairs as well. And that's just good. That's just absolutely great, right? So all of that stuff has some life upstairs. So we haven't messed up in some sense. But why is upstairs better? Because, well, it's not just one vector space, right? So downstairs you just have a number, but it's a whole isomorphism class of vector spaces. Some of them might be more appropriate for your problem at hand. And it's not just small or equal, or there's not just one map, there's a whole set of all matrices. So upstairs you have linear algebra, the whole power of linear algebra, and there's just nothing comparable downstairs, right? So between 1 and 2, what can you do between 1 and 2? Essentially nothing. But what can you do between a vector space of dimension 1 and the vector space of dimension 2? You can put in 1 by 2 matrices. And there are plenty of them, and everyone likes to play with, maybe not everyone, but at least I like to play with matrices. So upstairs is linear algebra itself, and downstairs is just a set. And that's the whole power, and that's kind of illustrating the whole power of categorification. Much better and much richer structure is living upstairs, but still everything you have downstairs is nicely reflected. I hope that makes some sense, because this is really, I think, a really good picture of categorification. And today I will just go through my various bias tour, focusing on the history, and the history essentially goes along, at least in my very biased perspective, along 2 key points: homologies and actions. And here's another categorification if you want. So you could think of a knot somewhere and another knot somewhere, and in the classical picture there's just no relation between them. But in the categorified world, you could put a surface between them, right? So knots 1-dimensional, surfaces 2-dimensional. So you've got up one structure, one level, in this case just 1 dimension. And that's another example of categorification. Now you have a richer structure, it's surface between knots. And in case you wonder how to draw a surface between knots, we'll come back to that later. It's essentially living in 4 space, and in 4 space you can actually do that. But anyway, and these surfaces are, by the way, called homologies. But anyway, that's another example of categorification. We went up 1 level, in this case just 1 dimension, and we get a better and richer structure. It's a really beautiful example again. Less algebraic, more topological in nature, I guess. Okay, so we already had that picture, so I'm not going to get to it again, but I hope it's clear. We have this universe itself on upstairs, so linear algebra itself, and, well, the natural numbers downstairs. So in disguise, categorification is actually really, really old, right? So this picture, linear algebra, is not the newest kid in the block, but it's a very nice picture again. So let me say it again. Linear algebra is categorifying, or is a categorification. Categorification is not unique, so it's not the categorification, it's more a categorification. Anyway, linear algebra is categorifying the natural numbers, and linear algebra is just fantastic. It's just absolutely great. So who doesn't like this picture? If you've turned off the video now, then you don't like this picture, which is fair enough. But certainly I do like this picture a lot. Right, you have a richer structure upstairs, and really it's justified by its linear algebra. So all of linear algebra is just absolutely fantastic. And if you want to go one step further, if you're saying, okay, natural numbers, linear algebra, sums up, what is the next step? Well, the next step came up quite late. It's still 100 years ago-ish, but it's quite late. And the idea goes back to Hopf and Noether, so fun story here. So Emmy Noether had a very hard stance in the Germany of the 1920s and was what is called a Privatdozent, I think, or what was called a Privatdozent. I'm not quite sure about. If I get the history wrong, I will get the history wrong, but this is roughly the story. And as a Privatdozent, which is not quite the same as a professor, you're supposed to give lectures, but you're somewhat more paid. So the students will pay for your lectures. So usually what people did is they had kind of easy lectures. So you get lots of students. Emmy Noether was kind of doing exactly the opposite. And well, Emmy Noether's lectures were not famous to be easy. So essentially, Emmy developed research ideas during lecturing, which is very impressive, by the way. And one of the top students was Heinz Hopf, sitting in the audience in Göttingen in the 1920s. And they essentially developed this whole idea underlying algebraic topology of singular homology. Just absolutely fantastic. And it categorifies the Euler characteristic. That's not the language they used. It was a little bit too early for that. Well, like 70 years too early or something. But anyway, essentially that's what they did. Right? The Euler characteristic, this famous invariant of a polygon, so the polyhedron theorem due to Euler, quite old. This was really bad. Let me give him another shot. Quite old. And it has a natural categorification on a richer structure, which are groups, homology groups. And you can do even a little bit better if you know this story. So a little bit later, so you can define singular homology groups without knowing a chain complex. And the notion of chain complex actually came later. But with chain complex, the Euler characteristic even becomes an alternating sum of dimensions. I will have a nice example in a second. But anyway, that's kind of the story where the integers show up. So the integers, the linear algebra categorifies the natural numbers known for a long time. But now you have this alternating sum, so you can also get negative signs. So kind of homological algebra categorifies the integers. This was kind of the next step on this way. And here's a kind of a nice picture. So if you have the sphere, then the Euler characteristic of the sphere, well known to Euler and many other people, like the old Greeks, without kind of having the right terminology, is just 2. It's just the number 2. The homology is, well, it's a much richer structure. But if you decategorify with an alternating sum of dimensions, we have 1 minus 0 plus 1, you exactly get 2 again. Right? So that's what I mean. The Euler characteristic is categorified by the homology. Really beautiful picture. And you get the minus signs because you kind of can go through the degree of the chain complex by alternating the signs. So that's how you get the negative signs. And therefore, homological algebra is a categorification of the integers. So kind of the next step, right? Instead of solve for x, that's like natural numbers, you now solve for x, that's like homological algebra. Anyway, homological algebra, obviously, again, maybe not obviously, certainly not obviously, but again, it's just pretty successful. And just again, the justification here, why categorification is so important, because homological algebra is so much richer than just the integers. So this is really beautiful. So, and again, you can argue that all the natural structures have some reflection upstairs, direct sums, tensor products, and so on. So it's really a good picture. And this is how the homologies entered. And this is essentially why categorification is so intrinsically related to topology, because topology, to a big of its part, is about homologies in some form or the other. Right? And why is this great? Okay, so here's a good reason why this is great. Okay, homology is somewhat better invariant than the Euler characteristic. It's a richer structure. Blah, 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 blah. You can play around with it a lot, and that's all good. That's fine. Not complaining. That's all good. I take it. Good. But the main upshot, at least from my perspective, is now you have a categorification. So you should be able to talk about the next layer. And indeed, the next layer here is that homology is a functor. So it talks about continuous maps as well. right? So it's really just, you have this picture of two categories, and you have a functor between them. And the functor is not just doing something to objects, like the Euler characteristic, but also to maps, which is really the new layer here that you cannot see using the Euler characteristic. So that's kind of my main upshot of this categorification of the integers. Now you have a functor and not just a number. And a functor is just a way richer structure than just a number. I hope that makes somewhat sense to you, right? So next layer, the new information, the morphisms, the continuous maps in this example. You can see them using homology. You can see them using categorification, which is somewhat the whole point of categorification too. Okay, and so where was categorification now really born? These are kind of examples that were around for a long time, but they were called categorification later on. They kind of were too early for that time, if you want. So where was categorification really born is here in the intersection of low-dimensional topology with many, many, many other fields, like von Neumann algebras, so functional analysis, where Jones, the person here on the picture, this one here is Jones. And in the background, you see 1990. So this picture is where Jones got the Fields Medal and kind of happily walks away with the Fields Medal in 1990. And Jones essentially got the Fields Medal for the discovery of the polynomial with the same name, the Jones polynomial. And why was that a great discovery? Well, that was a fabulous discovery because it kind of revolutionized knot theory, but also connected various fields. So absolutely fantastic discovery and one of the cornerstones in mathematics and in mathematical physics, and nowadays even beyond. So really great. It's a polynomial that can be used to detect knots in a certain sense. So certainly getting the Fields Medal is absolutely fantastic. And well, this discovery got Jones the Fields Medal. And then people started to wonder whether there's actually a categorification of that picture. And that was essentially how categorification was born. So not much later, not that much later, maybe a little bit later, whatever, Kobanov found this famous categorification of the Jones polynomial, which is now homologies theory. Kind of you could think of this as graded, and there's an extra grading giving you a variable down below. That's why you get a polynomial and not a number like in my Euler characteristic example, but it's essentially the same type of example. It's just a categorification that was not known before. And this breakthrough is just absolutely fantastic. And many, many people study that, and it turns up in various different fields. It has this ridiculous number of citations for a maths paper, a pure maths paper, like a really pure maths papers. They don't tend to have many citations. 1,500 is quite an impressive number. Anyway, and it's really rich structure. So it's kind of this bi-graded theory that you can see here in the background, the Romanov homology of this torus link. It's quite a rich structure. It's a really rich structure that Romanov discovered here about, 25 years ago, 24 years ago. And this was really the birth of categorification. So this was already called a categorification. Then, as you can see here, the title of the paper, a categorification of the Jones polynomial. So singular homology was clearly first, and it was never called a categorification because it kind of was before its time. But people in the mid-90s, end of the 90s, used the term for the first time, and Romanov just cooked up this one, which really kick-started the whole field of categorification. Now it's just like a big industry. And it really categorifies this famous polynomial of Jones. So it's a better invariant, and exactly for the same reason. So homology is a better invariant than the Euler characteristic. That is all good. So in this case, the Euler characteristic of Romanov homology is the Jones polynomial. So homology is a better invariant, thumbs up. But actually, it's a functor. And Romanov homology is the same. It's a functor. Link homology knows about cobordisms between links. And here's a nice picture that I obviously stole of cobordisms between links. So if you have whatever those links, there's a nice cobordism between them. You have a saddle cobordism just changing. So what you see here is always the boundary of the picture next to it, and the natural surface you draw it in between. And all of these look like they intersect, like this one here, which goes from open to crossed. But in 4 space, you could think of them as being actually very far apart. So in 4 space, they don't cross, and cobordisms are always built out of some basic pictures like this. But anyway, the whole point is it's again the same story. For one of homology is a function and not just a polynomial, right? The Jones polynomial can't see that. And that's really a nice type of categorification. Right? Application, this is now doing in four-dimensional topology. Here's another picture. You have a link at the bottom or not, and you have a link at the top or not, and you have cobordisms between them. It gives you now a map between complexes or a map between homologies, whatever you want. And it is just extremely great. And it has some applications and expected applications in four-dimensional topology, which is completely invisible from the viewpoint of the Jones polynomial, which is again the whole point of categorification, right? It's now the next layer. In this case, the next layer just goes up one dimension, not in free space, and here we have a four-dimensional kind of a four-dimensional invariant that we can cook up from for one of homology. Really beautiful example. So this one of homology is now around for 25 years, and then people try to, well, do various things with it, in particular to try to understand where it comes from. And during that, people developed categorical actions. And now categorical actions kind of live above representation theory. They kind of replace usual actions in a certain sense. And the whole idea is roughly the following. So not too long after the Jones polynomial was discovered, Reshetnikhin-Torayev gave a very famous construction, a theoretical construction of the Jones polynomial, or of all Jones type polynomials. There are whole families of those guys, essentially. And essentially, the idea is you slice your knot into basic pieces, like on this side here. Each basic piece corresponds to a specific linear operator between spaces. And those linear operators turn out to be equivariant with respect to a certain group action or algebra action. So in this case, SL2 or quantum SL2. And essentially, that shows that this part of low-dimensional topology is the same as representation theory, and the fields really merged, and they're really now hard to separate. They're essentially the same. So you can play not theoretical games by just slicing your knot into basic pieces, and you can just evaluate on another side by just computing linear maps, essentially, which is an absolutely great idea. And what turns up here is that, well, the representation theory on this side determines the properties of those polynomials. And that's why there's an action involved. There's an action of a certain type of object, in this case, a quantum group, quantum SL2, or more generally, whatever acts. And people took that as an indication, so kind of the same type of picture, and then Crane and Frankel eventually conjectured something related to higher dimensional cobordisms. So from this picture, you can cook up a three-dimensional TQ of T, and the categorification of a three-dimensional TQ of T should be somewhat a four-dimensional TQ of T, and they then coined the term categorification roughly around the mid of the 90s, building on this earlier work of Reshetnikhin-Torayev, and therefore categorification is kind of intrinsically related to actions of certain objects. In this case here, the Jones polynomial that's Reshetnikhin-Torayev is representation theory of SL2, the Lie algebra or the group, whatever you want, or rather its quantum version. So the task that was opened here is, well, what about one of homology? Shouldn't it be some kind of categorical action or something? So maybe categorify representation theory itself, right? So not just categorify like the natural numbers or the integers or a certain polynomial or whatever, but categorify a whole theory. And that's now the idea of categorical actions. So it's a field that categorifies in certain sense, in some certain very precise sense, representation theory itself, which was born in this way by kind of mimicking the Reshetnikhin-Torayev thing for covariant homology in a certain sense. So essentially the idea is that here was our polynomial. It was vector spaces and linear maps, vector spaces and linear maps, the little slices of my picture. So what should be a categorification? I hope you remember my little picture from upstairs. So how can you categorify vector spaces? Well, you can replace them by categories. How can you categorify linear maps? You replace them by functors, and then you always have the next right? I showed you this step here as my beginning example, and there's a next step where you go now really to categories. And in each step, you have a new type of object that appears that you can't see before. And the history of the subject is a bit rich. I'm nearing the end of this video, but many people have worked on this. And it started roughly around a little bit later, maybe, than kind of one homology itself, trying to explain the appearance of one homology, which is mostly related to this piece here. But it can vary. You don't need to have Lie algebras or Lie groups acting. You can think about group actions in general. You can think about finite dimensional algebras acting or whatever. And you just get many, many theories which roughly look all the same. And they're all very rich and very applicable, but they are kind of different in details, which is exactly the same as how representation theory works. You have different flavors of representation theory, whether you're studying Lie groups or monoids or algebras or whatever. They all look kind of the same, but they're then a little bit different. And it's really, really the same here. And this story has been like ridiculously successful. And there are many, many, many works and many, many papers and many, many breakthroughs related to this story, including proofs of old conjectures or giving new proofs or whatever, just connecting fields and really rich. Way too much to be covered here in this little afterwards recorded video, in case you remember. And then for me, what really is the point, I said again, that you should build a theory, you should kind of build those theories, but at the same time you should apply it, and then having applications will give you more examples to improve the theory. And having a theory, then you can apply it to to applications, and then go around in this little circle. And there's just many, many, many examples how the theory is applicable. There's a whole categorification, for example, of the representation theory of the symmetric group, which is arguably the most important kind of representation theoretical object you could study. Okay, let me just wrap up. For me, apply theory, build theory, apply theory, build theory, apply theory, build theory. Plenty of applications. I listed a few more recent ones here. Cryptography of machine learning, for example. Anyway, I really hope you enjoyed this video. So here's a summary. So categorification kind of really originates in studying homology and is therefore intrinsically related to, well, anything related to topology and category theory, because category theory was born out of topology. Anyway, and if kind of the point is a mixed connection visible, there's a new layer of structure, and it gives you really more tools to apply it and to do something people weren't able to do before, which is just really the whole point, right? Let's think of the step from the natural numbers to linear algebra. Linear algebra is just a new way, completely new way of attacking problems. And in a less large framework as a linear algebra, that usually happens with categorification. On a smaller scale, of course, so if you just write one paper on something, this is usually a little bit small scale, but you should expect something along those lines to happen. Anyway, I really hope you enjoyed this talk or video or whatever you want to call it, and I also hope to see you next time.